A hungry bear doesn't dance. You've heard the saying, right? But here's the thing. It's not just folk wisdom. It's actually a law of physics. If you want to swim for an hour, you need fuel, say 5 bananas worth of energy. Without that fuel, you're not going anywhere. Your body simply runs out. Our bodies are machines, biological engines that convert one form of energy, food, into another form, movement. That's why bears need to eat, and that's why you do too.
Cars work exactly the same way. You probably know how much fuel your car burns per 100 kilometers. It depends on the make and model, of course.
In other words, using gasoline or diesel, you can move yourself and whatever cargo you're carrying from point A to point B. It's another machine converting one type of energy into another.
Cars and us, we're actually remarkably similar. 2 machines obeying the exact same law of physics.
The law of conservation of energy.
In its simplest form, this law tells us something profound. You cannot create energy from nothing. You cannot destroy energy into nothing. You can only transform it from one form into another. That's it.
And nearly everything in the universe, everything, obeys this fundamental law.
But why should you care? What's the point? Well, let's take a topic that's usually explained in the most boring way possible and actually make it make sense.
First, let's clear something up. The law of conservation of energy and energy conservation, as in saving energy, are not the same thing.
When we talk about energy conservation, we mean things like insulating your home or taking public transit, saving money while helping the planet.
But the conservation of energy, the physics law, has nothing to do with saving. It's entirely about where energy comes from and where it goes.
Let's start with the textbook definition. Here's how they usually put it.
In a closed system, the total amount of energy is constant. You cannot generate more energy than what already exists within the system. You cannot destroy the energy that's already there, but you can transform it from one form into another.
Now, let's break down what that actually means.
First, a closed system. Think of it like a perfectly sealed box. No sunlight gets in, no heat escapes, 0 interaction with the outside world. Nothing in, nothing out. And if we strip away the formal language, the law of conservation of energy is basically the physics version of no pain, no gain. You want results? You have to put energy in first. If you want something, you have to work for it. If something needs to happen, it requires effort. Otherwise, and Newton's laws back this up, an object in motion stays in motion, and an object at rest stays at rest.
Welcome to Physics Meets Motivation 101.
I know, this still feels a bit abstract, so let's bring it down to earth with some real-life examples.
Now, as someone who's been obsessed with cars since childhood, a true petrol head, let me explain this the way I know best.
You've got a car. You pull into a gas station and fill up the tank. Right now, you've got something close to a closed system. All of your energy is sitting right there in the tank, stored as liquid chemical fuel.
You start the engine. Fuel is fed into the combustion chamber where it ignites with oxygen. And just like that, chemical energy becomes heat energy.
The burning fuel creates hot, expanding gases that push the pistons down with tremendous force. Heat energy has just become mechanical energy.
Then what do the pistons do? Well, through the crankshaft, gears, and drive shaft, they ultimately spin the wheels. Mechanical energy becomes kinetic energy. And just like that, you can drive to the store and buy milk.
But as much as I love combustion engines, I have to be honest about something. Vehicles running on gasoline, LPG, and diesel are incredibly inefficient. If cars were 100% efficient, you could skip all those intermediate steps and convert chemical energy directly into kinetic energy.
But at every single stage, at every single conversion, significant energy is lost.
Some of that energy is lost to friction, metal grinding against metal. Some is lost as sound. Yes, sound. Because sound is a form of energy too, and it has to come from somewhere, right? And whatever energy survives all that, it's still not entirely at your service. A huge chunk of it is lost to air resistance. So if you add up all the energy you actually used, the kinetic energy that moved you forward, plus everything lost to friction, air resistance, sound, and heat, you get back exactly the amount of energy you started with.
In fact, let's put some numbers on it.
You start with 100% chemical energy. The amount you actually use to move, a mere 15%. Roughly 74% is lost as heat inside the combustion engine alone.
About 6% goes to electronic systems like air conditioning, and another 5% is lost in the drivetrain, the components that actually turn the wheels.
And this is exactly why, as much as I love traditional engines, we need to say goodbye to the old combustion era and embrace electric vehicles and alternative fuels.
We see this law everywhere in daily life, like when you boil water in a kettle.
Electrical energy flows from the outlet into the heating element at the base. As current passes through, it heats up rapidly. Electricity becomes heat.
That heat transfers into the cold water. Before long, the water starts to boil. And if your kettle switch is broken and it keeps going, the water starts to evaporate. You might ask, where's the conservation of energy in all this? Well, most of the incoming electricity is converted into heat in the water, but some of it is used for something hidden, the latent heat of vaporization, the energy needed to turn liquid into steam. Add up all the electrical energy that went in and compare it to all the thermal energy the water gained. They're nearly identical.
But not exactly the same. Why? Because a kettle isn't a perfectly closed system. Some of that original energy escapes as sound, that rumbling you hear, and some radiates out through the body of the kettle as heat you can feel with your hand. So once again, perfect efficiency is impossible.
So, let's talk about proof. How do we actually know this law is true? Well, first of all, it just makes sense. That's not proof by itself, of course, but think about it. If one log keeps a fire burning for an hour, what happens when you add 2 logs? You'd expect it to burn for 2 hours.
The more energy you put into a system, the more you get out. And in a closed system, input equals output, always. But in science, because it makes sense, isn't good enough. So how do we actually prove that the energy at the start equals the energy at the end?
One of the first people to answer that question was James Prescott Joule. To find what he called the mechanical equivalent of heat, Joule designed a brilliant apparatus, a set of paddles inside an insulated water container connected to a falling weight.
He calculated the potential energy of the weight, the energy it possessed simply because of its height above the ground. And according to his measurements, when the weight was released, nearly all of that potential energy was transferred to the paddles in the water. As the paddles spun, they churned the water, heating it up through friction. And with this, Joule could calculate exactly how much energy was needed to raise the temperature of a specific amount of water. And his calculations confirmed it. The energy gained by the water was exactly equal to the energy lost by the falling weight. That's why, to this day, we measure energy in joules, named after the man who proved conservation of energy in a lab. And the man who inspired Joule's work, Count Rumford, born Benjamin Thompson. While working in German munitions factories, Thompson noticed something everyone else had missed. When cannon barrels were being bored, they produced enormous heat. The common belief was that this heat was a hidden property of the metal itself. But Thompson realized the truth. It was friction.
the mechanical energy of drilling was being converted into heat energy. Joule himself later acknowledged that while their methods were different, their conclusions were remarkably similar. Now, at this point, you might have heard some people claim that nuclear reactions create energy from nothing, that they violate the law of conservation of energy.
But no, nuclear reactions do not violate this law.
It might sound unbelievable, but do you know how we know? From this.
E equals mc squared. How beautiful. How simple. How universal.
Anyway, in short, what Einstein tells us with this formula is that energy and mass are the same thing. You probably already knew that. So when we talk about the conservation of energy, sometimes we're also talking about the conservation of mass. A nuclear reaction starts with one set of atoms and ends with a different set. During fission or fusion, heat energy is also released.
If you measure the mass of the atoms before and after the reaction and add in the heat energy that was released, they're exactly equal. The conservation of energy is not violated. Because mass is just another form of energy, you can't create it from nothing or destroy it into nothing, just like energy itself.
I know. I went off on a few tangents again, but I hope it all made sense.
So, in summary, the more you want to swim, the more bananas you need to eat. Can we say that? I think we can. And as always, until we meet again, I'm glad you're here. With love.